Hello, everyone. Good morning. So, the three talks today, this morning, will be about theoretical computer science. Theoretical computer science serves as a very good example of how basic science can change our world. Uh, it aims to understand the nature of computation. So, as a consequence of this understanding, it provides more efficient methodologies. So our first speaker today is Professor Venkatesan Guruswami from UC Berkeley. So he graduated from MIT, then he became a Miller Research Fellow at UC Berkeley. So before he came back to UC Berkeley, he held faculty positions at the University of Washington and Carnegie Mellon University. He was also an invited speaker at the 2010 ICM. So today he's going to talk about when and why do efficient algorithms exist. Let's welcome.
Thank you very much for the invitation, the introduction, and especially thanks to the audience for coming this early in the morning. It's certainly a bigger audience than I expected, so thank you very much. So I have structured this talk as a fairly broad talk. Hopefully, it will be accessible, at least most of it will be accessible to all of you. Feel free to ask questions in between if something is not clear. So I've structured this talk with this somewhat audacious title on when and why efficient algorithms exist in computer science, but really the case study will be for problems like constraint satisfaction and related variance. Okay, so I'll start very gently. Let's start with a task which is very easy to solve with an algorithm, which is that suppose I give you a graph. And undirected graph, and I want to color its vertices red or blue, and the idea is that I don't want adjacent vertices to get the same color. Okay, it's a simple problem, and this is the same thing as checking if the graph is bipartite, two colorable, and of course there is a very simple strategy. If you think about this, it's a very simple algorithm for this. You can start by coloring some node red, that forces its neighbors to be blue, then their neighbors have to be red, their neighbors have to be blue, and so on and so forth. And when you're done, if you don't have any inconsistency, then you have two colored the graph. If you fail, you must have found an odd cycle which cannot be two colored, as this picture shows, and that's it. So given a graph, you can easily tell if it has a two coloring or not in time, even linear in the size of the graph. Okay, so this is like really simple algorithm. Now, suppose your graph is not two colorable, like this pentagon here, then you need more colors. So now you can ask, given a graph, can it be colored with three colors, red, blue, green, so that the same property holds, that there is no edge with the same colors in the endpoints. And of course, the pentagon can be three colored. But if you try to do it for a general graph and a general algorithm, the trouble is that once you color a vertex, you still have two choices for its neighbors. So, this propagation algorithm quickly runs into this combinatorial explosion. Okay, so the naive algorithm, if you implement what I just said, will take 2 to the n time, because for each branch you'll have two choices. Now there are smarter algorithms known, better than 2 to the n, but they all take time exponential in n, something like c to the n for some c bigger than 1. In fact, the current record is something like 1.329. Okay, and indeed this is not an accident. We do know that three coloring is an NP-hard problem, so we expect that it should take exponential time. Okay, so 2 versus 3 makes a difference. Now let's come back to a two coloring problem, which itself is hard. Two coloring is nice because where vertices just take two values, red or blue, 0 or 1. So instead of graphs, if I talk about what is called as a hypergraph, then even two coloring gets tricky. What is a hypergraph? In particular, what is a three uniform hypergraph? It's the same picture. You have some vertices, but now edges are not pairs, but they are triples, like these blobs. And what is the two coloring problem? The two coloring problem is to assign red or blue to the vertices again, but now you want to avoid a monochromatic hyperedge or monochromatic triple. So if you take any triple, it must have both red and blue. And of course, if the triple, for graphs, this is the same as coloring, but this is one way to generalize graph coloring to hypergraph coloring. And this is also one of the very classic NP-hard problems in Karp's original list and so on. So this also is going to take exponential time. So what is happening here is something called, you see a dichotomous behavior. So if you take 2 coloring, it's very easy. 3 coloring or 2 coloring hypergraphs on the other hand is very hard. So on one hand you have polynomial time, in the other case you take exponential time, and that's a huge difference in complexity. So this is what we call dichotomous behavior. It's either kind of quite easy or really hard. Okay? There's no in between somehow. And turns out this is actually true for a natural class of problems. So that's the story I want to tell you today, and I will also try to give you an explanation of how that arises and where we can go further based on this understanding. All right. So that is the plan. But before I jump into that, I want to step back a little bit and ask an even more general question. So we have lots of computational problems. Why are some problems easy and why are some of them hard? So somehow for certain problems there is some mathematical structure which makes it easy, and somehow you lack that structure, it makes it hard. So we would like to understand this. Now in a way this is asking for a theory of everything for algorithms, right? Much like theory of everything in physics or something. And perhaps given that there is a huge variety of problems and many clever approaches to solve them, perhaps you shouldn't expect a universal answer. But there has been a major success for constraint satisfaction in some of its variants, and that's where I would like to go to in this talk. And some of the philosophy underlying that, which I illustrate with examples, is that to understand when a problem is easy, you actually look at some structure in its solution space. So if there is some non-trivial symmetry in the solution space, which will be encapsulated by something called a polymorphism, then somehow that leads to algorithms. Okay? And before I talk about CSPs, let's ease in with some examples from settings which you all probably are familiar with. Let's start with the quintessential algorithmic problem, which is easy, which you all learn in school, which is that solving a system of linear equations. You can take your favorite field or ring and you have a system Ax equals b in variables x, and you can of course solve this with Gaussian elimination. But what is the symmetry in the solution space? So it is this closure property. If I take 3 different solutions in this space, x1, x2, x3, then I can take x1 minus x2 plus x3, that will also be a solution. Simply because ax1 minus ax2 plus ax3 is b minus b plus b, which is b. In fact, any affine combination would be okay. Okay, I just picked this one because 1 and minus 1 are present in every ring. Okay, and this is captured by this fact that this function, which takes 3 ring elements and outputs, or 3 field elements and outputs another field element, f of ABC is a minus b plus c, is a polymorphism for the linear equation problem. What I mean by that, we'll get a little more clear later, is that you can take 3 different solutions and simply apply this function component wise for each variable without regard for other variables, and you will also get a new solution. So this gives a way to combine solutions locally to produce a new solution, which is a very non-trivial fact, and somehow that seems to make it easy. Similar story holds for another workhorse in efficient algorithms, linear programming, where you have Ax lesser equal to b for rational matrices A and vector b, and you're trying to solve or find if there is such an x. And here the closure property is the well-known convexity. Right? So this is a convex region. So if I take 2 solutions x1, x2, any convex combination, in particular x1 plus x2 by 2 will also be a solution. And so you have these polymorphisms which take a, b, and for example output a plus b by 2 if theta is half. And of course this is also solved by some non-trivial algorithms. Now I'm not saying that just the existence of this immediately leads to an algorithm. It's often a very non-trivial road to go from these closure properties to the algorithm, but at least it is prescriptive or suggestive that an algorithm exists, and then you can go and find it. And of course one of the things we would like to do is maybe make this link a little more descriptive as well, so we understand why such algorithms exist. Now I want to come back to discrete problems. Those were both continuous problems. Let's go back to our 2 coloring example. Here is a graph which has 2 colorings, and in fact it has multiple 2 colorings. It is disconnected. So here are 2 colorings for that graph, where I just pick red to be 1 and blue to be 0. Now the question is here are two colorings. Is there a way to combine them to produce another two coloring? Okay. And turns out the answer is yes. If I apply the majority function in each column, so majority simply means if two ones are there, you output 1, if two zeros are there, you output 0. If you apply this to each column, you get a new vector, and you can easily check that that will also be a true color. Okay. And that's not hard to see, because if I take, for example, V1, V2, in every row they are different. So the majority of V1 must be different from the majority of V2. Okay. So, and that means you have this closure property again. You can take two colorings, combine them by coordinate wise majority, namely this function is now a polymorphism. I'll define this formally for two coloring. And indeed we know that two coloring is solved by various algorithms, and in fact two coloring has other polymorphisms too. In fact, instead of taking majority, I can just add them mod 2. So I can output 1 if there is an odd number of 1s and a 0 if there is an odd number, even number of zeros, and that is also a polymorphism. Okay, so this is a problem with a lot of structures in the solution space, and as I will show later in the talk, this somehow corresponds to many different algorithms. Okay. Now, let me go back to this other problem, two coloring hypergraphs. So let's take a simple example of one hyper edge, and here are three different valid colorings because none of them are monochromatic. And now the question is, can I combine them to produce a new two coloring? If you can try majority, but of course that doesn't work, right? You get 0, 0, 0. Now you might think that, okay, maybe there is some other crazy function you can apply. Maybe you can take 12 different colorings and combine them and so on. But you can actually prove that in this case there is no interesting way to combine this. Okay, and this interesting qualification is simply because I can take a function which just outputs one of these rows, just copies rather than combines. Okay, and but that's sort of a boring function. Okay. And the same holds for graph 3 coloring as well, and indeed these problems are hard. Okay. So you can sort of maybe see where the philosophy is going here. So far what I have said is that these polymorphisms, which I will formally define soon, are local operations to combine multiple solutions to produce a new solution. And again, the remarkable thing is that for a rich class of constraint satisfaction problems, we now know, actually thanks to work by two people in this room, I'll mention that shortly, that assuming P is different from NP, you have efficient algorithms if and only if you have interesting polymorphisms. And I find this remarkable because it's a perfect example of this link between mathematical structure and computational complexity. You have precisely understood when algorithms exist for this class of problems. Okay. Okay. So to sort of make sense of this, I need to define what constraint satisfaction problems are and what polymorphisms are. And I will do both of these formally now. It will be a little notation heavy, but hopefully with examples it will be clear. So what is a constraint satisfaction problem? Now many of you have probably seen problems like 3-SAT and 2 coloring and other things. These are all CSPs. So most of you have sort of seen it, but this just encapsulates the class of problems. So you have a constraint satisfaction problem is parameterized by a finite domain D, say 0, 1, and a predicate of some arity from D. So it's just a Boolean function which maps k values from D to 0, 1. In general, you can allow multiple predicates, but for simplicity, let's just stick with one predicate for notational simplicity. Now CSPP is a problem. Okay, an instance of this problem consists of n some number of variables, and n is the parameter which grows, that's the size of the input, and you're going to apply this constraint p to certain tuples of these variables. So here I've taken k as 2, so really you take n variables and you're going to apply p to certain pairs. And the question is there a way to assign values to the xi's so that this formula is true? Same thing as saying all these constraints are satisfied because you're applying p locally. So it essentially asks if a collection of local constraints can be simultaneously satisfied. Much like a system of linear equations asks if many individual equations can be simultaneously satisfied. Same concept. Okay? The only difference compared to linear equations is that these are very local constraints. They only look at some k values. And an example, suppose P is this function which outputs 1 if two things are unequal and 0 otherwise, then this problem is nothing but graph coloring, because you can put a graph on these variables x1 through xn, and P x1 x2 is simply telling you that you must color x1 and x2 differently. So these are like the edges of the graph, and you're asking if this graph is two color, colorable with D colors, and if D is 0, 1, it's two color. Okay. Hopefully this is not too fast, but this is the CSP definition. I'll give many examples next slide. So in general, that's the problem. So in general, you might have multiple predicates, so the notation gets more complicated, but the philosophy is the same. You have a fixed small number of predicates, you can apply any one to any tuple in any way you want, that gives you a problem. Now the question then becomes is that when is this CSPP problem easy, when is it hard? Okay, before we come to that, let's see some examples. I already said graph 2 coloring is an example. You can take the predicate to be x not equal to y. If I want hypergraph 2 coloring, you have one predicate which takes 3 variables and says that they should not all be equal, because you don't want all of them to be 0 or all of them to be 1. So that is this. You have something called 1 in 3 sat. It's a variant of this 3 sat, where you say that exactly one of the variables should be 1, the other 2 should be 0. That's a constraint. So you can apply this to any triples you want, and you will get a 1 in 3 sat problem. And you can also encode things like graph connectivity by having these 3 predicates. Okay, it's not hard to see. And these were all Boolean problems where the domain was 0, 1. You can also have non-Boolean domains. Certainly you can have graph K coloring where you make the domain K. And there is a famous problem called unique games, which also is a problem over large domains where the predicates are essentially permutations. Okay. So these are all CSPs. Now I need to tell you what a polymorphism is. Okay. Hopefully any questions about CSPs? Okay, maybe I'll just leave it there for 1 second. I mean, this is horrible to read, so don't look at this. So the subscripts to 4 depth. Okay. So it's basically problems like 3 sat, to graph coloring, etc., abstracted in a general way. So what is a polymorphism? A CSP is specified by a predicate. So we are going to also define, so we are going to capture its complexity by something called the polymorphism of that predicate. So what is a polymorphism of a predicate? It's a function from D to the M to D, where M is some arity of the polymorphism, which can be up to you. If whenever the following happens, when is it a polymorphism? If the following holds. If you take an arbitrary set of M tuples which satisfy P of your choice, and then you take them, you apply your F. Now F can be applied to D, M elements of D. So you can apply F along the columns. Now apply F along the columns, you're going to get a new row, a new tuple that should also satisfy. Okay, I'll give examples in the next slide. So it's basically a closure property, higher order closure property. If I take M solutions and I combine them using F, I'll get a new solution. Okay, that's exactly what I've said down here. And the set of all such functions is called polymorphisms of P. Now you might wonder if this is even exists or is empty. It always exists because you can have these functions f of z which simply outputs the ith coordinate. What that means is that when I take these M tuples, I simply copy the ith tuple down here, and that's of course going to have this property. So these are called dictator functions because they ignore everyone else and just go along with one person. Okay, so these always exist. So this set is non-empty. Now the question is whether there are anything interesting besides dictators. Okay, so that's the point. Okay, so again, this is the definition. Another way to think about it is that if you take an M by K matrix whose rows satisfy P and you apply F column wise, you should get something that satisfies P. Okay, I just wrote down the definition. Now for 2 coloring, we already saw this, such a polymorphism exists. If I take 3 rows which satisfy, all the 3 rows are 0, 1, 1, 0, 0, 1, they are unequal, then applying majority will give me a pair which is unequal. Okay, so majority 3 is a polymorphism for this, which is non-trivial, not a dictator. Let's do one more example. And actually, thanks to Dimazouk here for mentioning this as a good way to motivate. So you might see it in his talk later too. So Pxy is 1 when x is lesser equal to y. So it just checks if one element is lesser equal to y in some the integers. And then if you think about it, you're basically saying if I give you pairs which are all lesser equal in each row, I apply f, I should get something which is also lesser equal. And if you, a moment's reflection will tell you that in this case, any monotone function is a polymorphism. That's the definition of a monotone function. Coming back to another example, if P is checks if there is an odd number of ones among a triple. So it takes 3 things and it outputs 1 if there is 1 or 3 ones, and 0 if there are 0 or 2 ones. Okay, in this case, what is a polymorphism? I can take 5 triples like this. Note that each row has an odd number of ones, and 5 just because it's an odd number, any odd number works. And I can simply take the XOR along each column, and that will also have an odd number of ones. Okay, and therefore this parity function on 5 inputs is a polymorphism. Why is that? Simply a parity argument, right? Each row has an odd number of ones and there are an odd number of rows. So the total number of ones is odd. So the number of columns with an odd number of ones must be odd. Okay. If you understood it, it's fine. If not, you can reconstruct it. So this is, in fact, any odd parity is a polymorphism. So these are all easy problems because they have non-trivial polymorphism. In fact, you can think about simple algorithms for these, and this particular case being Gaussian elimination or linear equations. Now let's go to this problem 1 in 3 SAT, where Pxyz insists that exactly one of xyz is 1. In this case, it's a nice exercise to prove that the only polymorphisms are dictators. Okay, you have nothing else, and that's just the story. Okay. Note that the last 2 slides have nothing to do with algorithms per se. You're talking about a particular predicate and closure properties of that predicate. So these are all like combinatorial mathematical facts. Okay, and now comes the link between these mathematical facts and computational solvability. Okay. So for this, what is the general goal? So if I give you a predicate P, or in general a collection of predicates, you would like to understand which CSP problems are easy and which ones are hard. 2 coloring was easy, 3 coloring was hard. 1 in 3 SAT was hard, odd 3 SAT was easy. Why is this happening, etc. And a very influential conjecture was made by Feder and Vardy in 98, saying that these CSPs exhibit this dichotomous behavior which I mentioned at the beginning of the talk. Every such problem is either polynomial time solvable or NP complete. Okay. So, and you have seen this in early classes, right? You see 2 SAT is easy, 3 SAT is NP complete. Okay, that's always happens. That's what they conjecture. And there was good reason to conjecture this, one of which is that already for the case when the domain was 0, 1, this was long known. From 78, Schaefer showed that if I take a Boolean problem, essentially the only easy cases are 2 SAT, Horn SAT and its dual, and linear equations, and some simple cases when you can set everything to 0 or 1, and everything else is NP hard. Okay, so he basically said that these are the only easy cases, everything else is hard. Okay, so if you have in your class seen algorithms for 2 SAT, Horn SAT, and Gaussian elimination, in some sense it says that there are no other algorithms for Boolean problems. Okay, so that was the story, but the general conjecture said this holds for every domain. And in fact, a stronger form or a more refined form of this conjecture was crystallized in the around 2005, which said that not only is this conjecture true, but it told when do you have an efficient algorithm. It said that the problem is in P if you have a non-trivial polymorphism, otherwise it's NP complete. So this tractability is completely governed and explained by polymorphism. So this is a stronger form of the conjecture called the algebraic dichotomy conjecture. Okay, and now, and again there was reason to believe this in the sense that for the Boolean case, this was exactly what was happening. If I looked at the tractable cases, each one of them had a non-trivial polymorphism. 2 SAT I already mentioned has majority of 3, same thing with linear equations, any odd parity. The other cases have Horn has and or, and these have the constant functions. So all the easy cases are explained by polymorphisms. So, and the general algebraic dichotomy conjecture said that this holds always. Okay, and this was open for a while till Andrei Bulatov and Dima Zook were both in the room here and are giving talks on these works with their FSA awards, settle this conjecture for all domains. And this conjecture has two parts, right? So, one is that if you don't have polymorphisms, you are hard. That was already known and in some sense is easier. The highly non-trivial part is the algorithm. How do you go from any non-trivial polymorphism all the way to an algorithm which solves every instance? And that's what they completed. It was a long journey, building on sequence of many deep works, which culminated in this. And somehow you have this very clear link. Okay, so and obviously, so this talk is, when I picked this topic, I didn't quite realize that they will both be giving talks here. But maybe it actually works out well because this gives you a sort of a higher level context and view of this body of work. And of course, for the real technical details, you can refer to their papers and talks. In particular, Zook is giving a talk this afternoon at 1:30, which I highly recommend. Okay, so now there, as I said, there are two parts. So I want to also talk about this conjecture and go further from that, but I will talk about it at a somewhat higher level. How does one show hardness? As I said, there are two parts, hardness and easiness. Let's talk about the hardness because the hardness is the easy part here. So, computer science power tool for hardness is reductions. You reduce one problem to the other. This is what we do with in our algorithms classes, reducing. This says that if B can be solved efficiently, then so can A, and we usually use it for hardness in the contrapositive form. So if A is NP hard, then B must also be hard, right? So this is what it means to show NP hardness. So in general, if you want to show some problem B is NP hard, you can take your favorite NP hard problem, for example, 2 coloring 3 hypergraphs, and just reduce it to B. Okay, and then that will show that that problem is hard. And how might you show such a reduction? Usually these are simple gadget reductions. For example, here is a gadget reduction showing that 2 coloring hypergraphs reduces to graph 3 coloring. So the way to do this is that you take a constraint not all equal XYZ. The hypergraph problem will say that these 3 things should not get the same color. Then you can put this little gadget graph here. Let me try to use this maybe. You put this gadget graph here. What should you do? So this is actually going to be the gadget graph. And you can easily see this works because if these 3 things get different colors, not all the same colors, you can color this inner triangle in a way where there is no pair which has the same color. On the other hand, if all of them get the same color, say red, then you're stuck because one of these things has to be red, and then that's a problem. If x, y, z are equal, you can't color the inner triangle. Okay, so therefore this graph is 3 colorable if and only if these 3 things got distinct values. So you're expressing one constraint in terms of the other, and this is often how you do gadget reductions. Now, what does this have to do with my story with polymorphisms, etc.? Turns out polymorphisms precisely characterize gadget reductions. Okay, so polymorphisms are the science behind when these reductions exist. Because you probably wondered this, right? Reduce one problem to the other, it looks like magic. Turns out you can reduce a CSP problem to another CSP problem if and only if, in a formal sense, P has more polymorphisms than Q. So in some sense, richer the polymorphisms, easier the problem. So that's one way to remember it. Okay, it gives you this. Now what this in particular means is that if I take a problem which has no polymorphisms, this is the hardness part of this dichotomy. If I take a CSP which has nothing, no polymorphisms, only dictators, then I can take P to be 2 coloring 3 hypergraphs. That also has no polymorphisms, or so that will reduce to this, and so you have shown NP hardness. So essentially, this shows that if you don't have any polymorphisms, you will have a hard problem which has more polymorphisms than you. It will reduce to you, and so you're hard. Okay, so this more or less basically allows you to finish the hardness part of the reduction. Okay. Okay, so there are some technicalities here on what trivial means, etc. But So I am hiding under the rug to get it correctly, but morally this is really what happens. Okay. So this is the hardness part. Now comes the algorithmic part, and this is in a way more interesting in some sense, because you're somehow saying you're taking mathematical structure and somehow elevating it to an algorithm. So here somehow the one key property is that if I take polymorphisms, I take many tuples in P, I get a new tuple in P. I can keep composing this operation multiple times because each time my output is in P, right. So using this, you can prove that polymorphisms have very rich algebraic structure. Okay, there is an area called universal algebra where these things are called clones. So they have lots of structure. And how this somehow plays out is that if there is a non-trivial polymorphism, for example, majority 3 or something, right, with some weak form of symmetry, then using some miraculous algebra, you can actually show that it has highly structured polymorphisms. And then those can somehow be exploited to give an algorithm. Okay, that's really the bird's eye view of this story. Now this, as I said, is highly non-trivial in general, and you should go to you should see Bulletauer, Zook's talks and papers to get a sense of how non-trivial this is. But I want to give a sketch the principle in a very baby case. Okay, so that's what I will do. And the baby case, I'll go back to my first slide, which is two coloring graphs. Now, graph 2 coloring can be expressed as a system of equations of this form. If I have an edge between I and j, I can put variables xi and xj and say that their sum should be 1. And let's say you solve it over 0, 1. So this exactly solves 2 coloring, right? Because if one of them is 0, the other one should be 1. So checking if a graph is 2 colorable is the same as checking if all of these equations are satisfiable. Now, in general, checking if equations are satisfiable over 0, 1, that's the NP-hard problem. Okay, so I can't just use this hammer in general, but I can do certain things. I can relax the problem. So what I can do is that instead of saying that they belong to 0, 1, I can say they belong to the interval 0, 1. And now you basically get a linear program, which you can solve efficiently, as I also explained in the beginning, using some methods. And now let us pretend for a second, and this is a big pretense, this is, it's a big deal, but let's just lie and assume that no variable gets 1/2. Then I can convert this fractional solution to a 0, 1 solution in a very natural way. If some variable gets more than half, I make it 1. If it gets less than half, I make it 0. Okay, and I'm just going to pretend I never get 1/2. Now this will clearly give a valid 2 coloring, right? Because if one variable is more than half, the other one has to be less than half because they sum up to 1. And this algorithm's working is somehow explained by this majority polymorphism. There is really nothing about 2 coloring which makes this work. It's really somehow explained by the fact that this majority function was a polymorphism for 2 coloring. Okay, so that is one algorithm. Here is another algorithm. I can relax xi to be, instead of 0, 1, I can relax xi to be any integer. Instead of saying it's just 0, 1, it can be an arbitrary integer. Now, another non-trivial fact is that system of linear equations over integers can also be solved efficiently. So now I'll get an integer solution, but I want to make it into 0, 1. How can I do that? Again, a natural rounding works, and here I'm not lying at all. This just works. If it's positive, make it 1. If it's non-positive, make it 0. And once again, 2 positive numbers can't add up to 1. 2 positive integers can't add up to 1. So you can't get both ones, and 2 non-positive numbers also can't add up to 1. So this will be a valid 2 color. Okay. And this, the fact that this works is again explained by a certain polymorphism called alternating threshold, which I'm not going to define, but it's basically like a signed form of majority. Okay. So there is, again, there is a whole class of problems for which an algorithm like this will work, which are all of those things which have this polymorphism. Okay. So again, the point I'm making with this slide is that there is a link between this problem having certain polymorphisms and it admitting certain algorithms. And you can see there's a third algorithm, and that's of course the simplest one in a way, is that you want to solve this linear system, just solve it. I mean, it's a linear system over the field of 2 elements, solve it over that by Gaussian elimination. And the fact that this works somehow is explained by the parity polymorphism, because parity function is linear algebra over F2. Okay. So these different polymorphisms lead to different algorithms. Okay. And 2 coloring is of course like has all of these polymorphisms, majority, alternating threshold, parity, it has different algorithms. But it turns out any one of these itself is, as I mentioned, enough to give you an algorithm. In fact, this is an instance of a more general result, which was few years old in work with Josh and Rockna and Zivny. We showed that for any CSP, or in fact it even works for a more general class called promise CSPs, which I will head to shortly. Any CSP with symmetric polymorphisms, which simply means that polymorphisms which are invariant under permutations of these variables. If you think about majority, it does not care what the order of the inputs are. Same thing with parity. So, any CSP with such symmetric polymorphisms has an efficient algorithm, and in fact the algorithm is a combination of the first two algorithms I showed you, the linear program and the solving system of equations over integers, affine equations. Okay, and the AT is not exactly symmetric, but it's almost symmetric. It's something called block symmetry. So this result really captures all these cases. Okay, so this gives you a little bit of a glimpse of this link between polymorphisms and this. Okay, I have a couple of slides on how this algorithm works, but I'm not sure I'll have time for it in the end. We'll see. Okay, so that's the story for CSPs. Okay, and in fact there are many other variants of CSPs. So far I have talked about, is there a solution satisfying all constraints? You can ask other problems. You can say, can you find, maybe there is no perfect solution. Can you find me a solution which satisfies as many constraints as possible? Maybe that's hard. Can you approximate that number? Can you count the number of solutions? And you can also ask more fine-grained questions. Now, for all these variants, there are some suitable form of polymorphisms which have been shown to be the link to algorithms. Okay, so CSPs, it's a very robust thing. It's not an accident that this happened. So it's really very robust. And what I want to tell you in the remaining part of the talk is a new exciting chapter called Promise CSP, which somehow seems to push this connection between polymorphisms and tractability even further and takes it into new territory, which seems to open up very exciting new challenges. Okay, so to tell you about Promise CSP, I'll go back to my favorite problem, graph 3 coloring. I told you it's NP hard to, we all know it's NP hard to 3 color a 3 colorable graph. What if I am allowed to use more colors? For example, what if I give you twice as many colors? I give you a graph, it's 3 colorable, but I know it's a tough job. So I say, hey, take 6 colors and color them. Okay. What do you think the complexity of this is? Easy or hard? If you said I don't know, that will be the correct answer, because indeed nobody knows. So for this problem, as simple as this, there is no efficient algorithm known, nor is NP hardness known. Now, it is true that we do believe very strongly that this problem is hard. We just can't show it, but we can show that it's hard under some very under some intractability hypothesis called D2-1 conjecture and so on. Okay, there's a line of work which in this final paper showed it under this conjecture. So we believe it's hard, but we can't show it's hard. And in fact, you might wonder why I put 6 here, because for 5 colors, indeed, it is known to be hard. So if I give you only 5 colors, it's NP hard. But even this was only shown recently in this beautiful paper a few years ago, and it really relied on this polymorphic insights and framework. Okay, so, and you might wonder what the best known algorithm is. That is way off. If n is the number of vertices, the best known algorithm, in fact, the record is from a paper in Stock, which is presented last month, is something like n to the 0.19 colors. So this is a humongous gap. Okay. So these problems can get hard. So these relaxed CSP problems are getting hard, and we would like to define a class of problems which captures this. And that's what promise constraint satisfaction does. Okay. And this was first formalized in this paper with Per Ostrand and Johan Hostad 10 years ago. And so basically we said, since coloring is hard and other CSPs are hard, can we consider relaxed versions of these problems? And how you can define it in very many ways, but this is what promise CSP will do. You will take a pair of predicates P and Q where P is stricter than Q. So P always implies Q. So now you will take your CSP instance like before, that let's call it phi strict. And now you will relax this instance by simply replacing all P's by Q's. Okay. So clearly if phi strict is satisfiable, so is phi relaxed, because the same assignment will satisfy it. So if a graph is 3 colorable, it's also 6 colorable. Right. So now the promised CSP, PCSP PQ is the following problem. I will give you this instance, I will promise to you that it has a satisfying assignment. And then it's hard for you to solve this because it's a hard problem. But I'll tell you, hey, can you solve it at least according to Q? So I can give you a graph, promise to you that it's 3 colorable, and ask you to 6 color it. And that is captured by this framework because 6 coloring is weaker than 3 coloring. Okay. So this is the problem, and note that when P is Q, you get back CSPs. So this is a strict generalization. And if you don't understand how can I promise something, another way to state this is as a gap problem. I'll give you an instance, I'll give you this and I ask you, is phi strict satisfiable or is even phi relaxed not satisfiable? You can answer that yes, no question, and that kind of is a decision version of this. Okay, but it's a little bit nicer to think of the search version, where you want to solve the problem by relaxing the constraints. Okay, it's a very natural thing we do when problems are hard. Okay. Okay, that's the problem, and let me give you an example in the next slide if this was a little bit puzzling. For that again, I'll go back to my 2 coloring hypergraph problem. Remember that for this problem, if I wanted to assign red blue colors so that no hyper edge is monochromatic, that was NP hard. So you can't do that. But now, what if I promise you that there's a stronger structure? What if I promise to you that there is a 2 coloring such that each triple has exactly 1 blue? So in general, you can have 1 or 2 blues, but I tell you it has only 1 blue. There is a coloring with exactly 1 blue, and that's the case in this coloring, for example. Okay. Now, in this case, it's still hard to find a coloring which has exactly 1 blue. That is the 1 in 3 SAT problem. That's also hard. But under this promise, I can ask you, hey, can you now find a coloring which avoids a monochromatic triple? So I'm making your life easier. I give you the stronger guarantee and ask you for this weaker requirement. What's the deal? Turns out now the answer is yes, you can do it. Okay. In fact, the algorithm is so simple in hindsight that I can just tell you what the algorithm is. It just fits in this box, right? So here is what you do. So you have a variable for each vertex here, and for each triple, you write this equation x plus y plus z is 1. With the idea that if x is 1, it gets blue, and if it's red, it gets 0. And I know the system is satisfiable over 0, 1. That's my promise. But of course, I can't solve this over 0, 1. That's hard. Let me solve it over integers, affine equations. And once again, I do my same rounding. All the positive values, I make it blue, and the negative values, I make it, or non-positive, I make red. And it works for exactly the same reason it worked for 2 coloring. Okay. And this is again explained by this alternating threshold polymorphism. In fact, that's how we discovered this algorithm. Okay. We found that it has this thing, and then we said, oops, there must be an algorithm, and then we found this. And there are also some other algorithms. This was not the first algorithm we found. And this example has played an influential role in this theory because it's a very concrete example. But again, this illustrates the point that the same algorithm, this is so similar to the algorithm for 2 coloring, and it works for, in this case, also because of the same polymorphism. So you really don't need to know. So the polymorphisms provide the link to algorithms in this sense. Okay. Having said that, I need to tell you what are polymorphisms. I only defined it for CSP. What are those for promised CSP? And your first guess would be the reasonable definition. You take a function d to the m to d. It's a polymorphism of the pair p comma q if the following happens. Take arbitrary set of m tuples satisfying p of your choice. Whenever you take them and you apply f column wise, you should get a new thing which satisfies q. Okay, so that's the code, and that's the PCSP. Okay, so far it looks very similar. So why can't we just lean on what has been done so successfully for CSPs? Somehow the issue really becomes that unlike for CSPs, these polymorphisms are not closed under composition because your output is a weaker object than the input. So you can only apply it once. It's a one-shot thing, unlike a polymorphism. And this somehow changes the game. You really have to deal with like polymorphism families. You can't just take one single polymorphism and amplify it somehow. Okay. So that somehow makes the game quite different. But they do have some structure. They are what are called minions. And I won't go into too much detail except for the fact that they have some closure property. So if I have a polymorphism and I set variables, sum of the variables to be equal to each other, I'll get a new function on a smaller number of variables. That will also be a polymorphism. So for example, if I have majority phi, I can go down to majority 3. So this has, so it's not like a completely crazy set of functions. It has some structure, but definitely much less structure than in the CSP case. And in fact, sort of understanding what structure you can expect is really the game. So having said that, there is a nascent theory emerging linking polymorphisms and promised CSPs, and of roughly the following form. If you don't have many polymorphisms, then you have hardness. And what does limited polymorphisms means? Basically, it says that if the polymorphisms are kind of boring and only depend on few coordinates, then you get hardness. On the other hand, if you have a rich enough set of polymorphisms, for example, the thing I told, if you have symmetric polymorphisms, family of symmetric polymorphisms, then you get algorithms. Okay, so this is the principle, and there are many examples. There should be more examples, but we have few examples. But the difference here is that it's really unclear what the dividing line between limited and rich enough means. In fact, it's not even clear what these are vague words, and there is not even a conjectured criteria on what that gap should be. And in fact, it very well could be that promised CSPs are just general enough that they elude dichotomy. So all these are possible things, which makes it very exciting to push this theory in this direction. Having said that, what has been done so far is that we have dichotomy for some interesting special classes. For example, we said, let's take the Boolean domain and let's consider P and Q which are both symmetric predicates, which means that they don't care about the order of the inputs. In this case, we do have a dichotomy. The algorithm is based on this symmetric polymorphisms, I said. The hardness is where the predicate symmetry is used. Basically, it says that you must lack certain polymorphisms, otherwise this algorithm will kick in. And if you are a symmetric predicate which lacks these polymorphisms, then these polymorphisms have to be kind of boring, which can then be plugged into some complexity theory machinery called PCPs to get hardness. Okay, obviously I'm compressing a lot here, but this is an interesting special case where we have a dichotomy. So perhaps it hints that dichotomy is not that crazy to hope for, at least in some cases. But this is pretty special. It's only Boolean, and it's only the case when P and Q are symmetric. Okay. Another case we can do is that I mentioned this because of this ordering predicate. Suppose your PCSP includes the lesser equal to predicate. So one of the relations is that x lesser equal to y. Why is this a reasonable thing to consider? Remember, I told you that in this case, polymorphisms must be monotone Boolean functions. And we really like monotone Boolean functions. They have a lot of structure. So using that, we do have sort of a dichotomy here. It's sort of a dichotomy because the hardness is under a very strong assumption. But you get algorithms when you have fairly symmetric polymorphisms where the variables have something called low Shapley influence, which is a very interesting notion from economics. That's also nice that you sort of open connections to other areas. And if you don't have such a thing, you can use that to show some sort of form of hardness. Okay, so this is another case where we have a dichotomy when you include the lesser equal to predicate. Okay, all right, so that's another case. Yeah, so I'm more or less towards the end of the talk. So I mentioned, maybe the one thing I want to mention is this result, which is like a fairly general result linking polymorphisms and algorithms. It basically says that for a promised CSP, if you have infinite family of block symmetric polymorphisms, then you have an algorithm. Okay, and block symmetric is not too important. Just think of these as symmetric polymorphisms. Okay, things like majority, parity, which don't care about the order of the input. And what is this algorithm? The algorithm is actually very simple. You run the basic LP relaxation. If it rejects, then definitely there's no solution. If it accepts, then run the affine equation algorithm, reject if no solution. If both of those accept, you accept. I'm lying a little bit here. There is some subtle issue on something you need to do between steps 1 and 2. But at high level, this is the algorithm. And this is really similar to the two columns I had for two coloring, the LP algorithm and the affine algorithm. You kind of have to do both and then it works. Okay, so that is the story. Okay, I'm just looking at how much more I have. Yeah, I'll try to. Okay, I'll just tell you what these algorithms are in general. So for example, I'll illustrate it for 2SAT, where you might have a constraint that either x1 or x2 should be true. So what you really do is that for the LP, instead of saying that the variable gets 0, 1 values, you say that there's a distribution of values on 0 and 1. So that's what this says. And likewise, for each clause, there must be a distribution on the assignment satisfying it. And you simply check that these are consistent, the marginals are consistent. Okay, that is the, and this is a system of linear equations. Sorry, this is a linear program because you have linear equations and inequalities. And because it is so, if the instance is satisfiable, it is satisfiable over 0, 1. So this is satisfiable as over LP. So this is how we will, in general, you will write a LP relaxation. And what is the affine equation? It's exactly the same as before, except instead of PIs, you now have QIs, which are integers which add up to 1. And the same thing for the clause. Nothing else changes. So instead of saying it's a convex combination, we talk about affine combinations. Okay. And then once again, in this case, due to classic results, you can solve the system. Now it's actually a system of equations. You can solve this. And again, if the instance is satisfiable, this must be satisfiable. So you check both, and then if not, you. So I'm going to skip the analysis in the interest of time, but it's really not that difficult. You have to be a little careful. But you essentially do the analysis locally. So if you have a particular clause, you line up enough copies of the different assignments, and you prove that the rounding algorithm, essentially, for example, this majority, if you have a majority function, you say that you can use that to round this in a consistent way, so that each constraint will be satisfied. Okay, so this will take some time to fully explain, but this is just a bird's eye view. Okay, so I'll leave it at that. But it's sort of an exciting frontier, because one of the things, the hope is that maybe some variants of this algorithm can solve even more general cases where you don't have a fully symmetric polymorphism. Okay, that's one of the frontiers. Okay, another interesting thing which has emerged from this work is that I said that this algorithm works when you have symmetric polymorphisms, but one can actually prove a converse. It works if and only if it has this thing. So if it lacks symmetric polymorphisms, this algorithm will in general not work. And that has been very interesting, because there is something called an abstract minion which captures this algorithm. And somehow we can then say that this algorithm solves the problem if and only if that minion, if your polymorphisms have more, if that minion is sort of smaller than this polymorphism. Okay. So really what I'm trying to get at here is that it's nice because it's not just question of which problems are solvable. We also are getting some understanding of the power of specific classes of algorithms. For each algorithm, like linear programming or semi-definite programming, or this particular combination of linear programming and equations, we have some abstract mathematical objects which somehow explain when those algorithms work. Okay, which is also nice. So you're kind of getting a mathematical understanding of the power and limitations of algorithms. Okay. And I think that's more or less towards the end of my talk. So I want to finally go back to one very bad loose end in my talk, which was this two-coloring algorithm based on linear programming. Right? So I said you write these equations, xi plus xj is 1, solve it over rationals, and just pretend that you don't get 1/2. But of course, that's a very bad thing to pretend, because in fact, everything equal to 1/2 always satisfies this. So the LP is absolutely useless in detecting if a graph is two-colored. Okay, so definitely that's an issue which has to be addressed. So the question is, can we somehow avoid variables getting a value half? Okay, and there are various ways to do it. For example, one way is that you can set one variable to be 0 or 1 and solve the remaining variables, and do that for every variable. And this gives you a way to jiggle solutions so that you move every variable away from 1/2. So you can play such games. But there's also something a little more elegant you can try, which is that, can you solve this system over a ring which avoids 1/2? Okay. So 1/2 was your enemy. So why not solve this over, for example, this ring z root 2, square root 2 adjoined to 2, where the only rational numbers are integers. So it does not have 1/2. And turns out you can do this. And again, this shows to have some polymorphic inspiration why this might work, is that I said the LPs are solvable because of convex combinations. Now you can make a convex combination with coefficients in this ring. Both these numbers are between 0 and 1. So this perhaps tells you that, oh, there might be an algorithm for this, and indeed by inspecting known optimization methods, you can make it work. And now you have no problem. All variables will be either more than half or less than half, and you can solve it. Okay, this might be the most complicated graph two coloring algorithm there is, but at least it shows that there are various ways you can think about algorithms. Okay, so many people I want to thank. I want to first thank Per Osten and Johan Hostad, with whom we introduced promised CSPs in this this paper, which is called 2 plus epsilon sat is hard, and actually a lot of people in the universal algebraic community have provided a lot of have motivated us and given us a lot of encouragement to pursue this, and they themselves have jumped in and done some beautiful work. Many of those works I mentioned here. So thanks to that, but special thanks to two of the students with whom I did most of the work I've done in this field, which is Josh Brackenseek and Sai Sandeep. Okay, so that's it, and I'm ready to summarize. So the broad goal in theory of computing is to say, classify problems as easy and hard, but you could take a more scientific lens and ask, why is something easy, why is something hard? And for these constraint satisfaction problem and many variants, we have a very satisfactory answer that you have this polymorphic principle. Interesting polymorphisms lead to algorithms, and their lack, leads to hardness. And now we would like to push this further, because CSPs, while beautiful and general, are not everything. And promised CSPs seem like a very nice direction to go for various reasons. One of which is that it really blends together many of the influential methodologies we know. From algorithms, it talks about optimization techniques. From hardness, it pushes the PCP techniques. And a third cog in this wheel is really the algebraic machinery, which was so successful for CSPs. How do we push it for here? Okay, and perhaps even more broadly, you could say that if you have to have any hope of solving the major questions like P versus P space, etc., you really need to understand this beast P. There are clever algorithms. We need to understand what polynomial time is, and perhaps pushing the boundaries of this further can give us some insight on what polytime computation is. Okay, and yeah, thank you.
Okay, thank you very much for your excellent talk. Any question?
Hi, thanks for the nice talk. So when did Hastad introduce Promise CSP? Is it recent or like 2 decades ago or something?
Oh, which one? The Promise CSP?
Promise CSP.
Yeah, I mean, it sort of formally was introduced in this paper AGH. We had with Per, myself, and Johan.
When?
10 years ago. Yeah, we studied a particular Promise CSP which we call 2 plus epsilon sat, and then we said that's a special. Of course, graph coloring was already known and studied, but given these two problems, this concept of PCSP crystallized. And then there were some more works, a few years later, which really couched it in the more algebraic framework of CSPs and so on. So,
thanks.
Say a few more words about like optimization, hardness of approximation, and its the relationship with like a polymorphism.
Oh, okay. Yeah. So there are two versions there. One is for optimization itself. You can say, find me an assignment which satisfies as many constraints as possible. So that is one variant. The other, and for that there is there are certain kinds of polymorphisms which lead to such thing. And I think basically it's known that either the linear program solves it or not. I think audience, as people might know better. And so that there is a polymorphic. So there you talk about polymorphisms which sort of take values, and then they should have something like submodularity, roughly speaking. That's somehow the submodularity, much like convexity, submodularity plays the role of leading to tractability. The other variant is approximation, where, for example, Prasad Raghavendra's result would say that if you have approximate polymorphism, there is a concept of approximate polymorphism you can define. So if there are non-trivial approximate polymorphisms of certain quality, the SDP algorithm will give you a approximation of the same quantity. So there is a precise link. Yeah.
Any question? So if not, let's thank Professor Guruswami again.
Thank you.